gas laws. Like I said, this is what is most useful. I hope that each one of you have a laptop up. If you haven't, quickly send one of your partnerships to go get one because you're going to need it. You can possibly use your phone too, so if you've got a phone, you want to have it out and ready to go. So let's talk a little bit, first things. Let's take a minute to research something. There was something that happened with gases in our community, and it's been a couple years, but phosphine gas actually killed 2 young children in our community. Could this have been avoided? Has anything like this ever happened before? So what I want you to do is I want you to do some research. I want you to answer the questions that are in these boxes, and they're also on the boxes in your notes. Okay? I'm going to give you 5 minutes. It's not a lot of time, so you're both going to have to work feverishly to do that. Look for phosphine gas killed 2 children, Layton, Utah. You can get up on KSL and look there. I want you to find as much as you can about it. Okay? I might give you a little bit more than 5 minutes. I said 15, so we'll do 15. That'll give you enough time to get things done. Okay? I'll bring up that timer again and reset it for you. Maybe. Bring another one up. About what you found out. So, what is fumitoxin, first of all? What is fumitoxin? Yes?
I believe it's a brand name for a pill that contains the phosphine gas when mixed with water.
Okay. What did you find? It's a pesticide. Okay, it's a pesticide. What was it used? How does phosphine gas work? He basically told us. When it's mixed with water, what happens? Fumitoxin. Toxic gas is released. That is phosphine. What is phosphine? It's in the same family as the nitrogen family, but it's pH3 instead of NH3 like ammonia. And it is toxic. What does it do? Yeah.
Kind of makes it like food poisoning like symptoms.
Gives you like food poisoning like symptoms, okay?
We found that mixed with the acids in the digestive system. Toxic gas.
Okay.
It attacks the nervous system through the skin.
Good. It attacks the nervous system through the skin or through inhalation. Why were the 2 youngest and not the older children and the parents affected in this family? Somebody else? Yes.
Because babies crawl on the ground.
Okay, babies crawl on the ground and that gas is heavier, so it stayed near the ground. Yes.
It's a smaller body, so it just takes less gas to.
Smaller body takes less gas to affect. Yes.
We found that their home was approaching immediately harmful life thing, but that was compared to an average adult, not to kids. So the kids couldn't handle that.
Okay. What else do you know about kids? How many have been around kids? They put things in their mouths. What else do? They eat dirt, okay? But they also breathe faster than we do. As you get older, you breathe slower. And little kids breathe faster, and so their air exchange, their gas exchange was a lot more than what we would get. So even though they were closer to the ground, more gas was there, they also breathed in faster and got more toxins into their body. Okay? Why was it put in the yard in the first place? Why was fumitoxin put in the yard in the first place? Yes. Okay, to get rid of the voles. What are voles? They're sort of like field mice. They're a little bigger than field mice, yeah. Okay, how was it cleaned up? When they found out that was the problem, how was it cleaned up?
Well, I found somewhere that they like dug up the soil and like mixed it with water to get it all out.
They did dig up the soil and they did mix it with a lot of water.
I was just confused why they mixed with water because I thought that released the toxic gas.
It does. And they put some big fans in there and they blew it all away. So they did evacuate the area and they did blow it away because what was happening is there was an area where the toxic gas would have gone into and stayed because there was a sink near them. And so they needed to blow it away, and the more dilute it gets, the more it doesn't harm people. So, okay. So this is something that has to do with what we're going into right now. And had the homeowner known anything about what was going on, do you think he would have allowed that to happen? No. Was he trusting that the people that came to his house knew what they were doing? Okay, you guys are going to become adults pretty quickly if you're not already 18. What happens is I, as an adult, am responsible for what I allow to happen on my property. If I don't understand it, then I better be asking a lot of questions. If I don't understand it, we just did a whole bunch of Google stuff right here, right? How long did it take us? 15 minutes, 10 minutes. What did you find out? Was this the first time this happened? It was not the first time it happened. So just because somebody says it's safe, should I take their opinion? No, it's up to me to keep my family safe. And so if something's going to go on in my house or around my house, it's up to me to research it before I say, okay, yeah, go ahead. Okay, so this is what we're going to be working with today. It was really scary. The family thought they just had the flu. How many of us have been sick this last month, and just had the flu-like symptoms? That's what the mom thought. She even took him to the doctor, and the doctor says, yeah, it's nothing. And then the next time she took him, other things were in play. And by the time they got him down to primaries, there wasn't much they could do. So it's sort of scary and sad. A lot of things are still going on with that. So let's go on and talk about some things that we need to with this. So when we talk about observed properties of matter, what two elements are liquid at room temperature? We've gone over this once before. What are they? Mercury and bromine? Yeah, bromine. Okay, what elements are gas at room temperature? Remember, bromine is a polyatomic, or not a polyatomic, but a twin, and mercury is the other one. Okay, what elements are gas at room temperature? These are the yellow ones. The noble gases, we know this, right? NOF and chlorine and hydrogen. So NOF is nitrogen oxide fluorine. We need to know these. Our liquids are sort of dispersed a little bit, but we need to know what they are at room temperature. That means the rest of the table is what? Solid. So most of the periodic table is solid at room temperature. Okay? Do you need me to wait a little bit longer? You got them. Okay, so here's a little grid that I had put on your thing to help you with some of this. There are 4 physical properties that distinguish between solids, liquids, and gases. The first property we're going to talk about is density. If the density is high, we've got a solid. Liquid is usually high, but lower than a solid because it has some movement that goes around there. And a gas is very low density because there's not very much there. Another property that we look at is shape. A solid has a definite shape. Okay, that's why it's called a solid. A liquid is an indefinite shape. It sort of takes and conforms to whatever is holding it. Okay, it doesn't fill it, but it conforms to whatever's holding it. A gas takes the shape of the container and fills it. So if I put something in a gas in a container, I've got to have a lid on it because it will fill the whole container. Another property is how compressible it is. A solid, is it very easy to compress a solid? No, it has a very low compressibility, very small. What about a liquid? Does it compress very easily? I hope not, because that's what we use in our brakes, right? And if it was easily compressed, then the problem would be the calipers would never close and our brakes would never work, because that's what we use to close our calipers on our brake. And then for gases, we can compress those a lot. And with the new cars that are running on hydrogen, they compress them a lot so that they can have a lot of gas in a small amount of area. Okay, the last thing that we're going to talk about is thermal expansion. So how much does it move when it's heated? That's what thermal expansion is. For a solid, it's not very much. It can move a little bit, can grow a little bit. When it's cold, it might shrink a little bit. For a liquid, it's also small. Okay, with the exception of What one expands when it's freezing? Water. Water is the exception to the rule. Okay, and gases for thermal expansion are moderate. So if I heat a gas up, it starts moving, and it gets a little bigger. Okay, so if I take a balloon and I put it in the freezer, it's actually going to shrink. If I bring it out into a hot day, it's going to expand. All right, we okay to move forward? If we got these? Okay, so we're going to calculate the volume of 125 grams of seawater with a density of 1.303 milligrams per milliliter. This should be easy. We did density at the very beginning of the year. Remember what the formula is? Your little dance if you're in love, right? Mass over volume. Okay, so we've got density equals mass over volume, and that's where we had the heart. We cut it in two. So if I've got density and I've got mass, because this is my mass and this is my density, and I'm looking for volume, what am I going to do? Nope. Mass divided by density. These two are going to trade places. So I'm going to times both sides by volume and divide both sides by density to get volume by itself. So plugging in, I would take 125 grams divided by 1.03 grams per milliliter. Grams will cancel. I'll end up with milliliters. Somebody's got a calculator real quick or a phone, punch that through for me. Get the answer. We are going to be using calculators, so if you haven't got one out, get it out now. 121.36, so 121.4. We'll actually only need 121, but that's okay. So we need to be able to find density. This is going to be important, and be able to use density. So let's look at this next problem. Copper metal has a density of this at 20 degrees. Now that's important because if we do different temperatures, then they can expand or decrease a little bit in size, so that affects the density. Here it has a density at this at 100 degrees. Calculate the change in volume that occurs when a 10 centimeter cubed piece of copper is changed from 20 to 100 degrees. So I'm actually going to have to find the volume at two different temperatures, right? Well, we just did the volume up above, so I can do the volume at 20 degrees and the volume at 100 degrees. And I'll do the mass at 20 divided by the density at 20 equals the mass at 100 divided by the density at 100. So for the first one, the mass was always the same, right? Mass didn't change. Mass doesn't change. So 10.0, that should be, calculate the change in volume. That should have been grams. Sorry, let's change that to grams because that shouldn't be centimeters squared. Grams divided by, and then we got 10.0 grams divided by, on the top one, the density for the 20 degrees was 8.92 grams per centimeter cubed. And on the bottom one, it was 8.83 grams per centimeter cubed. Okay, grams are going to go out. We should end up with 1 point something on both of them. Units being centimeters cubed, centimeters cubed. Somebody figure out what the answers are for me. Let's go 3 sig figs. Okay, everybody agree with that one? Okay, bottom one. 1.13. So the difference is 0.01 centimeters cubed, right? Because it wanted to do the change, so I just do the difference. If I subtract these two, I would actually do the 1.13 minus the 1.21, but I would say there was a change of this much. That is my change in volume. And remember, a triangle means change. Okay? The bob and weave, that's the bad thing about being in the back. Sorry. Yes?
So what just happened was a thermal expansion?
Mm-hmm. Thermal expansion. Because we were heating it up. So as it got hot, it increased in volume.
So the test, they're going to be like solve the thermal expansion.
They could say that. Okay, so let's talk about kinetic theory. I like to use ways to remember this because it's hard to remember all of this by itself. So we're going to talk about what's happening with kinetics, but I'm going to give you a way to remember it a little bit different than the real way. Okay, so thermokinetics basically says as gases are moving around, they're going to collide with each other. They're also going to collide with a wall. When they collide with a wall of a container, that's where we measure our pressure. Okay? So, as they're moving around, some things like our twins or our diatomics stay together. Other things are separated. But when we have diatomics, they run around in pairs. So here's the postulates, and I'll try and give you my way to do it right after. So if you don't want to write it down right now, you'll be okay. So these are the long ways. Gases consist of tiny particles, atoms or molecules. These are particles that are so small compared to the distance between them that the volume size of the individual particles can be assumed to be negligible or zero. The particles are in constant random motion colliding with the walls of the container. These collisions with the walls cause the pressure to be exerted by gases. Hang tight. The particles are assumed to attract or are not assumed to attract or repel each other. And the average kinetic energy of the particles is directly proportional to the Kelvin temperature of the gas. That's a lot of ugh. So, think of a toddler. These are 5 rules. Toddlers are considered people under 5, right? Toddlers are, this is my short version, the toddler rules. These are talking about particles in an ideal gas, and most people think that toddlers are so cute and lovable and always doing the right. I know, sometimes they aren't. It's okay. They have no volume. Basically, we don't have to pay for their seats. They can sit on our laps. Okay? So they have no volume, or very, very minute. They have elastic collisions. Have you ever watched a kid that's just learning to walk and they fall down? As long as nobody's looking, do they get right back up? Yeah. But if somebody's looking, then you get the cry. Okay? So as they bump into things, we call them elastic collisions as long as nobody's looking. Right? So, next thing is, are in constant random straight line motion. If you've ever watched a toddler, it's like, oh, cool, I'm going for this. And then they get to whatever it is and they look somewhere else. Oh! And they find something else to go to. And then they find something else to go. Their attention span is like minute, right? But they see something they want and they head right to it. So if I held a teddygram up for my little grandson yesterday, he was right there at it. He grabbed it from me and then he took off after a truck. So, I mean, attention span, nothing. But they are in constant random straight line motion. They don't attract or repel. And I hate telling you this story, but it will prove a point. When my kids were little, we went to the store. And my kids had not been exposed to very many different cultured people about that time, okay? And they saw their first black person. And my daughter, bless her soul, said, "Mommy, how come she didn't take a bath?" And she said it loud enough for the lady to hear. I was dying. They don't have any filters. There's nothing. They're not repelled by people. Why didn't she take a bath? And then later she saw a person that had tattoos and rings all over their place, and she says, "How come you write it all over yourself?" You know, but she wasn't scared of him. She wasn't put off by him. She still went and talked to him. She wasn't really attracted or repelled. Okay? So little toddlers, they don't have this preconceived notion of stay away from that person or go to this person and, oh my gosh, what are you saying? No attraction, no repel. Okay? So think of that when you're talking about 5. And they have average kinetic energy directly related to the Kelvin temperature outside. So this is how I remember this. If it's cold outside, they want their blankie, they want to snuggle. If it's hot outside, I want to go outside and play. I want to play on the swings. I want to go to the park. They want to go. But when it's cold outside, they're not too much. They might go out for a little bit, but then they want to come in and get snuggled. Right? 5 years old or less. Okay? So these are what I call the toddler rules. These are the ideal rules for an ideal gas. Okay, so get real. Life is not ideal. They grow out of that cute little stage where you're frustrated with one moment and then they're so cute the next, right? You get out of that, right? So get real, teenagers, here they come. Oh my gosh. Here's the teenage rules. Particles in a real gas. How are you different from toddlers? So you take up space, right? You take up space. You have to pay for a spot. You have your own volume, right? How else are you different from toddlers? You are attracted and repelled by people, right? Some people you think, oh, he's cute or she's cute and I want to get near her. Or others are like, oh, no, thank you, right? Okay, so you're attracted and repelled. Now, how can I make teenagers more like ideal gases? When are they most ideal? It is summer. Oh, and collisions are not elastic. You guys do find that out. There should be one more point there. Sorry, there's not. I should put that 3. You learned that in driver's ed, right? Or before? Collisions are not elastic. When you crash into something, it's going to cause a problem, right? Okay? All right, so gases behavior is most ideal. So in other words, when can I make teenagers most ideal? Summertime, when it's low pressure, I don't have any tests I have to take, and high temperatures, right? That's why it's summer. Okay, so this is how I remember it. If it helps you, great. If not, then just memorize it. Okay, toddler rules, 5 of them. Who can tell me the toddler rules? They brought the paper so you don't have to go to the copy center. Who can tell me the 5 toddler rules without looking down at the paper? Give me one of them. Yes. No volume. Okay, there's 1. 2.
Elastic collision.
Elastic collisions. 3. Come on, give me 1. Okay, 3.
Like attract or repel.
Not attracted or repelled. You already gave 1. Somebody else has got to do it. I got 3 of them. Okay, cheat. Look at your paper. What are the other 2? You can't tell me. Somebody else.
They don't attract or repel.
We already did that one.
Dang.
Yes. Constant, straight line motion, man. I want this. No, I want this. No, I want this, right? Okay, what's the last one? What's the last one? Yes. Average kinetic energy related to temperature outside. Cold, I want my blankie. I'm not moving much. Hot, I want to go outside and play in the park, right? Okay, all right. Teenagers, oh, I'm going to, oops. And your nonpolar molecules. In other words, you can choose who you hang with. I forgot that one, sorry. You can choose who you hang with. You don't have to be in a classroom with people you might not like, right, or get along with. All right, so before we go on to the next one, I just shut that off. Don't look down. Teenagers, how are you different? You have volume. You attract or repel others. There was one more. Yes. Collisions are not elastic. We have driver's ed. Okay, how can I make you more ideal? Somebody else besides the front row here. Yes. Low pressure. Okay, what else? Low pressure. What else? Yes. High temperature. Yes. What else? I can choose with who I want to hang with. So a non-polar situation. Okay, so that is all represented by summer, right? Where you don't have school. Yes.
I'm a little confused about like what like the ideal conditions for it's like an ideal gas.
An ideal gas.
So like what you would want a gas to be.
What you want a gas to do and how you want it to act. Yes.
Like stable wise, like it's
Stable or just in general how you want it to act, and we'll go. You'll understand more in just a sec. Okay. Yes.
Wait, so I don't know the difference between like the toddlers and the ideal client.
Okay. So toddlers are when we have everything is ideal. The summer thing is when I'm getting real gases to act more like ideal gases. Okay. Does that make sense? So I'm making the teenagers act more ideal and happy again. Yes.
compromise for realism.
Something like that, yes. Okay, so let's define these. So kinetic energy is the energy a particle has as a result of motion. So I have to move. Kinetic energy is energy of motion. And we use the kinetic energy equation 1/2 mass times velocity squared. That's not volume, that is velocity. Lowercase v is velocity. Okay? So if you need to make yourself a note there that that is not volume, do it. It's kinetic energy equals 1/2 mass times velocity squared. So how fast am I moving? Potential energy is the energy a particle has as a result of an attractive or repulsive forces acting upon it, but it's not being in motion. It's what I have potential to have. Okay? So it's not being used right now. Like, you have the potential to do well in this class. Are you using it? Have you got some kinetic energy going? Or are you just sitting there at potential? Cohesive forces are things that are attractive forces between particles. It is associated with potential energy. So cohesive forces are holding it together forces, and they're part of our potential. And the last one, disruptive forces. These are the forces that result from a particle moving. It's associated with kinetic energy. So the bottom one with kinetic energy, the middle two to go together. So top and bottom go together, middle two go together. I'm seeing the bob and weave still go on, so.
How is cohesive forces related to potential?
Because it's things that hold it together. They haven't been broken. The energy has not been released. So it's a potential to have energy, but not been released yet.
And what's the difference?
Disruptive forces are the ones that as I'm moving, something's happening. I'm changing that force. I'm pulling something apart. I'm moving something on. Okay? Yes?
So is kinetic to potential as disruptive as
Yes. Yes. Okay, going forward. What is the equation for kinetic energy? We just did it. What was it? Good. 1/2 mass times velocity squared. That's kinetic energy equation. You're going to need to know that. Suppose that a ball is thrown up in the air with such it goes straight up and then falls and is caught by the person who threw it. Describe the changes in the form of energy that occur from the ball from the time it's thrown to the time it's caught. So what's happening here? Okay, so this is kinetic energy, right? And disruptive forces. What happens when I get right to the top? It hasn't gone back down yet. It's just basically stopped. Right here is being potential energy, which is also known as cohesive forces, right? At the very top. When I go back down, what's happening? Motion again, right? So it's kinetic energy, and this becomes our disruptive forces. So I just use the picture rather than write out words. You guys okay with that? Okay. Going forward. So here we have football. Suppose we have a 180-pound, which is 81.8 kilogram halfback, running at a speed of 8.0 meters per second. Collides head-on with a 260-pound, 118.2 kilogram tackle running 3 meters per second. Which one will be pushed back? That is, which one has more kinetic energy? So what do I need to set up first? Does it matter which one I do? No. So let's do the first one right here. So kinetic energy of the 180-pound person. I'm going to have to use the kilograms. So remember, it was 1/2 mass times velocity squared. So 1/2 mass, 81.8 kilograms, times velocity, 8.0 meters per second squared. So that would be 64 times 81.8, and then divide it by 2. What do we get? Yep. So 64 divided by, or times by 81.8 divided by 2. Somebody got an answer? 8 squared. 8 times 8 is 64, right? Somebody got an answer for me? 3 sig figs. Yes. 2,610. The unit here is joules. A kilogram meter squared per second squared is a joule. So if you want to write that down so you remember it, that would be great. Let's do another guy, 260-pound dude. His kinetic energy is going to be 1/2 mass, 118.2 kilograms, times by 3.0 meters per second squared. So we've got 9 times 118.2 and divide it by 2. What do we get? Yes. 530 what? 31 joules. Which one has more energy? The first guy. So he's going to push back the guy that's heavier, believe it or not, because he's got more energy coming at him. So we'll say this guy is the one that's moving because he looks like he's moving faster. And this one's the one that's not, even though he looks skinnier, we're going to pretend. This one's going to actually push that one back. Right? He has more energy behind him.
Doesn't seem like it.
He's moving a lot faster, and you've got a lot more energy behind you. Yep.
How would you round on this one? Because you said 531, but it was 531.9.
It should be 532 then. Yep. Okay, and he has actually almost 4 times the energy the other one does. Okay, does that make sense? Okay, going forward, which would have the greater kinetic energy? Hydrogen molecules, remember hydrogen molecules are H2, traveling at a velocity of 2v, or helium molecules, and helium is not diatomic, traveling at a velocity of v. Ooh. So again, if we look at kinetic energy is going to equal the mass, 1/2, the mass, which is 2 times 1.008, right, times by 2v squared. For this one, somebody do that. We're going to end up with v squared as part of the units. On the other one, we're going to have kinetic energy, so that was for hydrogen. This is for helium. Whoops, He. 1/2, the mass of helium, I don't have memorized, 4.0026 times by v squared. So again, we're going to end up with v squared. What are we going to get? Yes? Because hydrogen is a molecule, meaning it hangs around in pairs.
Oh, but it says helium is a molecule.
But helium as a molecule doesn't hang around in pairs. Remember, only our diatomics hang around in pairs. Ron Hifkel? And then remember PS, by the way, phosphorus hangs in 4s and sulfur hangs in 8s. Okay, so what do we get for the top one here? Well, I can do this, cross those 2 out, right? 2's will cancel, and I get 1.002 times by 4. 4.032. If I do the bottom one, this will cancel this and leave a 2.0013, and there's nothing else there, right? So it's just going to be 2.0013. These squares are the same, so which one's traveling faster? Hydrogen is.
I get it. Why is it, well, the first one goes meter per second. How can you just switch it to velocity? Is meters per second the same as velocity?
Yeah, it didn't give me a velocity. It just says it was twice as much velocity. Right here, it just gave me this.
That is kind of meters per second.
It's a, I don't know what the velocity is. It could be meters per second, it could be feet per second, it could be whatever. It's some kind of velocity. I'm just comparing the two. So I'm just comparing the two. If I wanted to drop it out, then I could say the ratio would be this. because the V2s would cancel.
So because velocity is squared, it has a greater bearing on which one's greater.
Good. Yes, velocity does carry a heavier weight because it's squared. So let's talk about the states of matter. Most of you know what these are. You've had them since you were little itty bitty, right? Solid, liquid, gas. You know what they are, right? Plasma. What's up with plasma? Plasma is a charged particle. So it's not just a solid one thing. It has actually charged particles that are moving around in it. So it has positive and negative things going on. And that has a lot more energy than even gas does. Okay? So let's talk about each of these. Explain each of the following observations using kinetic energy, kinetic molecular theory of matter. So toddler rules. Okay? Gases have low density. How does that explain with our toddler rules? Itty bitty bitty and a lot of bit of space, right? So they don't take up space.
Is it also faster as it gets closer to molecules travel? Like a gas?
Gas has more velocity, yes, usually.
So the particles are
Moving faster, yes. So it's like wanting to play outside. Okay? All right, a gas always exerts uniform pressure on all walls of its container. What of the five would apply here? No.
Just sure which one A or B.
B. What do you think? Yes? No, that one actually wouldn't work here. It would work for the first one, yes. Yes, why? It's going to keep hitting the walls. So think if I took a tennis ball and I threw it at the wall and it kept the speed that I threw at it because it's elastic, right? So it's going to hit the wall and have the same amount of energy coming off. It's going to keep hitting the walls and keep hitting the walls and keep hitting the walls and going around. Now we know that it's not really going to happen because of friction, so that would be real, get real. But in an ideal situation, it would keep the amount of velocity going and it would keep hitting the walls at different places. So that would be an ideal gas. Okay, let's look at the last one. Solid, liquids, and gases all expand when heated. 5 toddler rules. Which ones does apply?
high temp.
The kinetic energy, yeah. So a high temp, it's going to move outside, it's going to move to expand, to go do things, right? Rather than sit and be cold, right? Okay, let's go forward. I know this is a big day of just lecture, but we'll try and make it go. Okay, the following statements are best associated with solid, liquid, or gaseous states of matter. Match the statement with appropriate state of matter. Temperature changes influences the volume of the state substantially. Solid, liquid, or gas? Okay, solid, liquid, or gas? Solid, liquid, or gas? Show me. Should be gas. That's a G, by the way, for sign. Okay, in this state, constituents, particles are less free to move about than in other states. Solid, liquid, or gas? Solid. Okay, solid. Okay, pressure changes, influences the volume of the state more than that of any of the other 2 states. Solid, liquid, or gas? Gas. It's gas. Okay, this state is characterized by an indefinite shape and low density. Solid, liquid, or gas? This state is characterized by an indefinite shape and low density. It's a gas. Liquid has a definite shape. It's whatever the shape of the container is. But gas will fill the container. Okay? So it doesn't have, we go through this. Whoops, sorry. Yeah, most of them are gas. Okay, gases expand to fill any container. Random motion, no attraction. Gases are fluid, like liquids, no attraction. Gases have very low density, no volume, lots and lots of empty space. Okay? So as we look at it, you look at the difference between solid, liquid, and gas. Gases over here have a lot of space between them. Okay? So here's some characteristics of the gas. Gases can be compressed. I can squish them. Okay? They have no volume, lots of empty space. Gases undergo diffusion and infusion, or effusion. Diffusion is when I take and I put perfume on and it goes away. Okay? Everybody can smell it. Effusion is where I have a small pinhole. So if I have a gas leak, I put in a sulfur-smelling thing, so even at a small amount that comes through that hole, I can smell it. And I know, oh, that's gas. I need to do something about it. So effusion is through a small hole. Diffusion is through a big amount. And that's because of the random motion. Okay, so now we go to pressure. Pressure is force divided by area. Force divided by area. So, what causes pressure? Collisions of the gas particles with each other and the walls of the container, that's pressure. So here we've got our example of figuring out that, oh, oops, collisions are not elastic. Okay, that gives us pressure. So this is a conversion thing that you will need to know. It is also on the back of your periodic table. We go back and forth between different volumes or different units of pressure. So 1 atmosphere is equal to 760 torr, which is equal to 760 millimeters mercury. Torr was actually the guy that set up that kind of pressure. That's why both of those are the same. 101.3 kilopascals, 29.92 inches of mercury, 14.7 psi or pounds per square inch, and 1.013 bar. Now you'll notice the difference between kPa and bar is about 100. You see that? It's 100 times to get to kPa. So we're worried about these collisions of particles, and we're going to measure them through we get that?
So torr and millimeters are the same?
Torr and millimeters are the same because that was named after the guy that did that. Okay, so let's do some conversions. The weather report on TV reports the pressure as this many inches of mercury. Calculate that in atmospheres, torrs, psi, bars, blah, blah, blah. So what we need to do is we need to use this on the bottom of our conversion factor. So it's sort of like what we were setting up to do our stoichiometry. I would take, for atmospheres, I would take the 28.6 inches. And on the bottom, I would put 29.92 inches. On the top, I would put 1 atmosphere. The inches would cancel, and I would get my atmospheres. I'm going to do the same thing with torr. I'm going to take the 28.6 inches, divide by 29.92 inches, but this time I'm going to use the 760 on the top for torr and get an answer. Okay, I'm going to give you, looks like the rest of the period. I can't remember what time we get out. We have 9 more minutes? Okay, let's see if we can do this in a few more minutes. Okay, so you're going to do that for each one of these.
Why is the 29.92 on the bottom of that one?
Because I want to get rid of inches. Every time I want to get rid of inches. And I want to go to something new. Right? So whatever I have, I want to get rid of. It's going to go on the bottom. Whatever I want to go to goes on the top. And this right here, these conversions, are where I'm going to get all those numbers. Okay? Because I can set up multiple fractions because they're all equal to each other. So 1 divided by the other is equal to a 1. Okay? Has anybody got the answer for the first one? 3 sig figs? Yes. 0.9 what? 56 atmospheres. So that's the first one. When somebody gets the second one, let me know. Yes. 726. Well, 0.5 will probably go 727 like the airplane. Torr. And what do I know about torr and millimeters mercury? They're going to be the same. So over here I can just go boom. Without any more stuff worrying about that. Okay, PSI. Do that next one. Let's see what we get. Yes. 05. Okay. I'm writing it highest because that back row was having a hard time seeing low.
Hey, I get it.
Yes.
Did you just write 29.92 on the top?
No, just on the bottom because I want to get rid of it.
Yeah, but at the same time, it's millimeters away, milliliters. Oh,
Okay. Those of you that got a computer out, you might want to start shutting down if you haven't already, and then put it away as you have a chance. So you're not all trying to get them put away at the same time. Okay, what about bars? Does anybody have bars done yet? That one should be close to the 28.6 because it's a 1 point. Actually, no, because we're dividing by 28. 29. So it should be close to 1. Anybody got it?
0.9.
Okay, and what was the difference between bar and KPA? Times it by 100, right?
So it's 96.83.
Good. All right, so this is where we'll stop for today. Now, next time we are doing a lab, but it's just going to be a lab. Well, no, it'll be a lab in the back too. We're going to do a quick one in here, and we're going to do one in the back that's really fast. But it is with pretty intense chemicals. We're using full-strength ammonium hydroxide, and we're using full-strength hydrochloric acid. So I'll be taking you back in small groups to do that while you're working on the other one in here. Yes?
is Wednesday's reteach going to be just
Wednesdays is just going to be, if you're having trouble doing any of this, we'll work on this. But we'll also, yeah, because I won't see you again until Thursday. So on Thursday, we're going to go into the actual gas loss.
I mean, I think I get it. I just want to
Okay? But you can come in on Wednesday and start working on your sapling.
Can I still come in Utah Science Day extra credit?
Mm-hmm.
I just totally forgot about it and I just remembered I have it.
Okay, any questions with this so far? We're good?